So this lab is called nuclear radiation, and in it we're just going to look at how radiation shielding works. There's something called the half thickness, but I'm going to start by just saying, so when nuclear particles decay, when we get radioactive decay, we see three basic particles. Alpha particles are helium nuclei. And so it's typically two protons and two neutrons. And these, this would be a heavy nucleus, so like we're going to be working with cesium-137 today. That's the 137 isotope of cesium. So it can throw out, that's its atomic weight, so it would throw out two protons and two neutrons if it lost a helium particle. If it lost a helium nucleus out of its nucleus, it's just a lump with two protons and two neutrons. So that would move its position in the periodic table from cesium, and it would reduce its atomic weight to 134. So radioactive particles often, for whatever reason, emit a helium nucleus, and that's called an alpha particle. The beta particle is an electron. And that's what happens when a proton sort of becomes a neutron becomes a proton plus an electron. And so a neutron in the nucleus will convert into a proton by spitting out an electron, and this guy will go out at high energy. Anytime they're spit out from the nucleus, they often have very high energies, and so they're very dangerous. It's really the kinetic energy of these guys when they leave the nucleus that makes them dangerous to us, because a helium nucleus can hit, if you're exposed to a radioactive material that has this, it can knock protons or neutrons out of the nuclei of an atom in a protein or something and change its behavior. And so it's just kind of random damage from these things that you don't want. And so these are really the most dangerous ones. These are next most dangerous. And finally, the gamma particle is a high energy photon. So most dangerous, least dangerous, most penetrating, least penetrating. So if you're exposed to helium nuclei, often just the air between you and the source will stop the particles, or at least your clothing will. Electrons take a little bit more. Just a sheet of aluminum will stop electrons. And then finally, what we'll be looking at today is what stops gamma rays, and it's much harder to stop them, but they're much less dangerous. And so you still don't want them, but the damage from them is less. And so we're going to be focusing mostly on this one today, and so what we're looking at is what happens to the intensity of the gamma rays So if I have a concrete wall or something like that, what happens to the intensity of the gamma rays on the other side of the wall as I make the wall thicker and thicker and thicker? And it turns out that the intensity obeys this formula. The intensity on the other side of the absorber is equal to the intensity on the side with the source times e to the minus mu x. X equals the thickness and mu is called the absorption coefficient. So today we're going to calculate the absorption coefficient for aluminum. We're going to be sliding aluminum plates in front of a cesium source, and we're going to figure out what the absorption coefficient is for this aluminum on cesium. And so the way you do this is you say, well, we're going to keep adding plates until the thickness gets to be, until the intensity is about half of what we started with, right? And so we're going to say 1/2 I naught, right? This is I. So we keep adding plates, and so here's our radioactive source, and we're just going to be adding plates in front of it, metal plates, which you'll see in a minute. And then here's our detector over here that's going to do the counting. And these guys are trying to get through, but some of them get stopped and some of them get through. And the thicker I make this, the fewer get through. Right? And so we're going to say, look, if as I make this plate thicker, eventually this guy will be half the initial intensity. And so that's equal to e to the minus, I naught times e to the minus mu times, we call it x 1/2 x 1/2 is called the half thickness, right? To get half the intensity, half the initial intensity, it takes the half thickness, right? And so the half thickness the half thickness is the thickness required to cut out half of the particles that are getting through. And so now my intensity is equal to half my incident intensity because my half thickness cut me down to 1/2. And so now I'm just going to write this up here. I'm going to say 1/2 I naught is equal to I naught e to the minus mu times the half thickness. Right, well, guess what? The I naughts cancel here, right? And so I get 1/2 is equal to e to the minus mu times the half thickness, right? Well, if I take the log of both sides, say the natural log, so the log of 1/2 is equal to minus the absorption coefficient times the half thickness, or if you remember, log of 1 over a is equal to minus log of a, natural log or regular log. And today we're working with the natural logs because we have an e here, right? And so this means minus the log of 2 is equal to mu times the half thickness. It's equal to minus mu times the half thickness, and then the minuses cancel. And so I get mu is equal to log of 2 over the half thickness, or it's equal to 0.693, which is approximately log of 2, over the half thickness. And so what we're going to do is we're going to calculate the half thickness, or we're going to do an experiment that's roughly going to give us the half thickness. We're going to determine it graphically, and then we'll use that to determine the absorption coefficient of aluminum with cesium-137. I wanted to say a little bit about the Geiger-Müller tube, right? This is this is how you detect radioactive particles, and it's actually very simple. A Geiger-Müller tube is usually a cylinder, right? Like this. So if you look at a Geiger counter, I'm going to get a Geiger counter out of my closet here so I can show it to you guys. This is a Geiger-Müller tube. Sorry, this is a Geiger counter. I think the batteries are dead in it. Yep. All right. But you walk around and you aim this thing at stuff, and then it'll give you readings. We use a little fancier version of it, but it'll just be a little tube that's sitting in a little case, and you'll see it in the next part of the lab in the next video. And so all this tube is this tube right here. It's got a wire down the center, right? And it's got some cable that goes off to the detector. And what happens is there's a big voltage between, this is at ground, and this might be at, I'll make something up like 100 volts. It's not that high. Maybe 10 volts or something like that. Something like that. And this is ground. And so this is positively charged. And this is negatively charged, the case is 0, whatever you want to call it. And so this is a positive, this will attract negative charges, this will attract positive charges. And so when these gamma rays, or these alpha, beta, or gamma particles enter in here, all they do is tear through the air in there and ionize stuff. It's just like throwing a baseball in through a china shop. Just debris occurs because these high energy particles come through here, and they cause electrons and atoms to be just strewn about. Electrons are separated from atoms, and then you get positively charged atoms floating around. So, little plus signs all over the place. I don't know how to describe it, right? And so these particles are floating around in the gas. These guys are attracted to the wall, and the negative guys are attracted to the middle. And so then this thing, the detector back here, the electronics back in here says, oh, we're getting charges on our wire here. And so it can count up and make a good guess at how many ionizations are occurring and how that relates to the particles going in. And so that's all that happens. These particles come in and create ions, and the ions are absorbed by either the wire or the wall, and those are counted up, and then that's translated into how many particles came in. And so it's pretty easy to count. You'll see how the counter works in the other room. I mean, in the other video. And by the way, there are smoke detectors that work like this, except almost the opposite. They'll put a radioactive source inside the Geiger-Müller tube, so it's creating a constant current. It's constantly creating a steady ionization in here, so that you're seeing a continuous current all the time. And then if smoke comes in, smoke is a great absorber of ions, of charged particles. And so if a smoke comes in, it'll trap the ions, and they won't be able to go to the wall, and the walls and the electronics will see that the current has stopped. And that's what triggers a smoke alarm. They don't all work that way. They used to all work that way, but a lot of them work that way. And so it's almost the same thing, except in reverse. Anyway, this Geiger-Müller tube is used for a variety of purposes, among them smoke detectors. What we're using it for today is just to detect radioactive decay events when particles get fired in.